So when we have a vector product of two vectors, A cross B equals C, let's compute that vector product in different coordinate systems. So let's begin by choosing two vectors I hat and j hat. And notice they're at a right angle. And because there's a unit vector, the area here is equal to 1. And I want to define k hat to be equal to I hat cross j hat. Now, our angle theta here was 90 degrees. And so if I use the right-hand rule, then I hat cross j hat is, the right-handed unit normal is out of the plane of the figure. And so I would write k hat like that. And notice k hat is out of plane of figure. And because I used my right-hand rule, this is what we call a right-handed coordinate system. Now, there's something very nice about this cross product definition. Notice that there's a cyclic order. I, j, k is a cyclic order. And if you interchange any two, for example, j, I, k, that's anticyclic. And the cross products satisfy this cyclic rule in that j cross k hat is I hat. And notice j, k, I maintains that cyclic order. And k hat cross I hat is j hat. K, I, j maintains that cyclic order. But because of the way we defined a cross product in general, A cross B is minus B cross A, because now you're using the opposite direction, so there's a minus sign. And therefore, any anticyclic permutation of these unit vectors, as an example, k hat cross j hat, has to be, notice I've what's called is minus I hat. That's anti-commutative property of the cross product. Similarly, I hat cross k hat is minus j hat. And lastly, j hat cross I hat is minus k hat. And so, in fact, you only need to know one. And this idea of cyclic and anticyclic to be able to write down all of the other 6. So we have 1, 2, 3, 4, 5, 6. Now, when you want to compute the cross products in Cartesian coordinates, for instance, it can be a little bit messy. There's going to be a lot of terms. If I write a vector A as ax I hat plus ay j hat plus az k hat, and I write a vector B as bx I hat plus by j hat plus bz k hat, and now I want to compute the cross product of these vectors to get the new one. Notice that there's going to be 6 terms because I have I hat. Well, we actually should say one more thing, that I hat cross I hat, the angle between these two vectors is 0. There's no perpendicular projection, so that's 0, as is j hat cross j hat, k hat cross k hat. So of these 9 parts, when we take the cross product, 3 of them will be 0 by this rule, and we'll apply our cyclic or anticyclic rules for the others. And so what we have here, let's just do it in, so C equals A cross B. And now let's just go one by one. I hat cross I hat. That's 0. The vectors, there's no perpendicular part. The area formed by these two vectors is 0. I hat cross j hat That's cyclic. ij is plus k hat. So our first non-zero term is ax by k hat, I hat cross j hat. And now let's do I hat cross k hat. Notice that's anticyclic ik minus j. So our next term is minus ax bz j hat. So there's the first two. And now let's just continue this process. J hat cross I hat, that's anticyclic. So we have minus ay bx k hat, ay j hat cross bx I hat. J hat cross j hat, that's 0. So we have no contribution there. And j hat cross k hat, that is cyclic. So that's plus ay bz k hat. And now we have our last two terms. K hat cross I hat, that's cyclic, so that's plus az bx j hat. K hat cross j hat, that's anticyclic, so there's a minus I hat, so it's minus az by I hat. And finally, k hat cross k hat, well, that's also 0. So we have 6 terms, and we can collect them equal to ax by minus, let's check this one. Here we use the wrong symbol here. We have to be a little bit careful here. ay cross bz is j hat cross k hat. That's plus I hat. So we have ax by minus ay bx k hat. And now let's look at the I hat terms. I'll just check those off. We have ay bz minus az by I hat, and check those two terms off. And lastly, we have az bx minus ax bz. So we have az bx minus ax bz, and that's j hat. And that's how we calculate the cross product in Cartesian coordinates.